Yo, bro, this is a waste of time, man.
No doubt it is.
Want to do an experiment?
We're experimenting. I bet, let's do it!
A few moments later.
Kobe! Kobe! Alright, Jason, what do we need for this experiment?
So we already have the sucrose and sulfuric acid.
Alright,
Can you go find some, or 2 beakers?
2 beakers? Yep, got it.
The aluminum foil should be like right there, yeah. And then
I got it.
gloves.
Gloves. Got it.
200 milliliter graduated cylinder, and then that's it.
Oh, got it.
Alright. Before you start, I'm just gonna do some like quick research so we don't die. So, this reaction is a dehydration reaction, and it's like super exothermic. And at the end, it creates like this crazy black thing.
Cool. So what gases does it produce?
It produces carbon dioxide gas, water vapor, and sulfur oxide gas.
Huh? Interesting.
Oh, and also, go find some sodium bicarbonate.
What? I thought you said this was it.
Do you want to die?
Yeah.
Oh, okay, well, can you just grab it so I don't die?
What is it?
It's just baking soda.
Alright, some right here.
Alright, that's good.
Alright, dope. Does this work?
Alright.
Eventually.
You ready to do this?
Yes, sir.
From this exothermic dehydration reaction, different gases are formed along with the creation of the black carbon. Water vapor, sulfur dioxide, and carbon dioxide gas are created from the large amounts of heat that are brushed onto water molecules. With stoichiometry, we determined that 4.58 liters of carbon dioxide and sulfur dioxide were created and 5,551.90 liters of water vapor was created with excess sulfuric acid. By determining that the enthalpy change in sucrose is around negative 918.9 kilojoules over moles, and the enthalpy change is negative in sulfuric acid, great amounts of heat are produced in this exothermic reaction, which substantially speeds up the rate in this dehydration reaction.
3 days later.
Alright, man. I will grab the sodium bicarbonate to neutralize this.
Alright, make it please. Here. Go faster.
Are we good? Alright, let's go. There you go, man. I think we can sell this.
Yeah, I think you're right, because we don't get paid for anything that we do in that classroom.
Yeah, let's go find some people to sell this to. Let's go.
The next day.
Hey, so I'm a student of LTHS with my business partner Kyle, and we're fundraising for our school because we're broke as shit. Let me show you our product that we made at school.
Wow, that's amazing work. Where'd you make that?
We made it at school.
What was your process in creating it?
So it's actually a dehydration reaction. It's a mixture between sugar and sulfuric acid. Okay, let me show you how it looks.
Here is the molecular structure for sucrose. Throughout the molecule, it portrays bonds between hydrogen and carbon, hydrogen and oxygen and carbon. Within the sucrose molecule, intramolecular forces such as hydrogen bonding are present due to the covalent attractive force between the hydrogen atoms and very electronegative atoms such as oxygen. Other intramolecular forces like London dispersion forces and dipole-dipole forces also surface the bonds of this molecule. In addition, this molecule bonds through the intermolecular forces of covalent polar bonding due to the stable balance of attractive and repulsion forces between the atoms. This is the molecule for sulfuric acid. As we can see, the intermolecular forces that are present are dipole-dipole forces, London dispersion forces, and hydrogen bonding. As mentioned earlier, different bonding is present due to the attractive forces between the different atoms in sulfuric acid. The strength of force is directly proportional to the increase in polarization of the molecule. By utilizing the measurement of electronegativity, It assists in determining the tendencies of an atom to attract a bonding pair of electrons. Due to the great difference in electronegativity in both sucrose and sulfuric acid molecules, these bonds are covalent polar, where the electrons that are shared throughout the atoms remain closer to the nucleus, causing a lower effective nuclear charge. With a balanced reaction, we were able to determine the theoretical yield for the carbon snake. From the 70 grams of sucrose with excess sulfuric acid, around 297 grams of carbon solid was produced. With the redox, it was easily determined that hydrogen was oxidized throughout the reaction, whereas sulfur and carbon were reduced. By determining the values for the Gibbs free energy, it gives insight to the maximum amount of reversible work on a reaction. The heat released by the oxidation of sucrose becomes sufficient enough to initiate the reaction as being a spontaneous dehydration reaction.
Yeah, I'll take one. I forgot the price, but is this enough?
Alright, let me check.
Hey!
Many months later.
Hey, what y'all doing?
Shit, go.